Like all living organisms, plants need food to grow and prosper. They have their own unique profile of nutrients that they need. And to feed crops, you need to follow 3 general steps. First thing, you want to look at the soil in which your plants are growing and determine how much nutrients are in the soil. Second, you want to look at the plant and determine how much nutrients that plant is going to need over its life. And then third, you want to apply fertilizer to make up the difference between what the plant requires and what's in the soil. And today we're going to be looking at that first step. That first step of gathering a sample of soil from a field and sending it to a lab to be analyzed to determine its nutrient content. Now this is an important question not just for farmers, but for everybody. Because if we apply too little fertilizer to a field, we get corn that looks like this, which means less food for us to eat. If we apply too much fertilizer, sometimes we can still get a healthy plant, but that excess fertilizer we apply to the land can be washed away with rain and enter our ponds, our streams, our rivers, our estuaries, and cause water pollution. So if we're going to feed ourselves and protect the environment at the same time, we need to apply just the right amount of fertilizer. And the only way to know that just right amount, that precise optimal amount, we need to know the nutrient content in the soil. To show you how this is done, I'm going to take you on a tour of the soil test laboratory here in the plant science department at Oklahoma State University. And on this tour, you're going to see why you learned a number of things in high school, like electromagnetic radiation and the structure of an atom, because those scientific concepts are necessary for determining the amount of nutrients in a soil. But before we get to measuring the soil nutrients, I want to talk briefly about what these nutrients are that plants need. Plants, all of them, need a large amount of hydrogen and oxygen, but they get that through water. Plants also need a lot of carbon. They're going to get that as they breathe in carbon dioxide, but sometimes, for reasons we'll discuss later, farmers do want to know the carbon content of the soil. And a lot of a plant's nutrients needs are amply provided in the soil. Things like boron and copper, there's usually more than enough of that in the soil for the plant to grow to raise crops for decades, sometimes even centuries. But most of the time, for farmers to raise crops and get a high yield, and when I'm talking about crops, I'm talking about things like wheat, corn, soybeans, things that farmers are planting and raising on large acreage with large tractors. Farmers are almost always going to need to apply the nutrients of nitrogen, phosphorus, and potassium to the soil, usually every year. And this is so much the case that when you hear a crop producer say the word fertilizer, they're usually just talking about nitrogen, phosphorus, and potassium. And indeed, a lot of the fertilizers you buy contain only that. This is a fertilizer I bought yesterday. It's a Miracle-Gro fertilizer. And when you look at its ingredients, you basically see 3 things: nitrogen, phosphorus, and potassium. Now, sometimes a farmer will have a field where they know that there's more than enough nitrogen, phosphorus, and potassium for the plant, but the plant still isn't growing well. And in that case, they may start wondering if there's not a deficiency of some other nutrient in the soil, perhaps zinc, perhaps copper. In those cases, she'll get a soil sample and she'll send it to the lab here at OSU. And in addition to asking for nitrogen, phosphorus, and potassium, she'll also want to know the amount of other nutrients in the soil. And if one of those other nutrients are missing, there are other fertilizers that contain more than nitrogen, phosphorus, and potassium. For instance, this is just another version of a Miracle-Gro fertilizer. And when you look at its ingredients, it still has nitrogen, phosphorus, and potassium, but it also has boron, copper, iron, manganese, and others. And finally, I want to say that when I'm talking about nutrients, I'm always referring to plant available nutrients. In any field, there's a certain amount of phosphorus, potassium, zinc, copper that is just not available to the plant, and there is some available to the plant. And when we do a soil test, when farmers take samples of the soil and send it to OSU, when we're talking about its nutrient content, we're talking about just the stuff that's available to the plant. And to see to see the difference between plant available and unavailable nutrients, let me give you an analogy. Imagine a river running through a canyon, and it's a fast-moving river. You know that as that river scrapes the canyon walls, it's going to be tearing away some of the soil with it. It's going to take some of the sand, some little pebbles, some clay with it. All that stuff that can be transported by water is, you can think of that as being the plant available nutrients, because for plants to take up nutrients, most of the time they got to take it up through water. It's got to be transported by water. But in that river going through a canyon, a large part of the canyon walls will not be moved by the river, at least not, say, in a year's time. It's going to stay sturdy by the wall. That's like the nutrients that are unavailable to the plants. So again, if I say we're talking about the potassium content of the soil or the copper content of the soil, I'm always referring to the plant available nutrients. This is a brief overview of how the soil testing process works. First, you need soil from the field that the farmer is raising crops. And a farmer is going to go out into the field and take soil samples from a lot of different locations in the field and mix them all together, get a representative sample from the field. And then they're going to pour that soil into this bag. They're going to fill the bag up, and then they're going to check on here what they want the soil test laboratory to measure. Now, almost all crop producers, or virtually all of them, they're going to mark that they want the nitrogen, phosphorus, potassium content of the soil analyzed, as well as the pH level, for reasons we'll talk about soon. If they suspect there's some other nutrient deficiencies, they might check for sulfur, calcium to be checked, or perhaps zinc and iron. And then they're going to take this bag and they're going to mail it to the soil test laboratory here. And the first thing they're going to do is they're going to leave it overnight in the oven at 150 degrees Fahrenheit so that the sample is completely dried out, all dry matter. And then in the morning, they'll come and they'll take out the soil sample, and then they're going to put it in a grinder and grind it to a fine powder. And then from there, that powdery, dry matter soil sample, it can go to a number of places. It could go to a machine that measures its nitrogen content. It can go to a machine that measures the other nutrient levels like zinc and phosphorus. It can go to a machine that measures the pH level of the soil, and it can go to a machine that measures the carbon content of the soil. For most farmers, the most important piece of information from the soil test is the nitrogen content of the soil. And that's measured using a flow injection analyzer like the one you see here. And it works basically like this. You have that dry matter of the soil sample, and then you mix it with a liquid solution. That liquid solution is designed to extract all of the nitrate. Nitrate is a compound of 1 part nitrogen, 3 parts oxygen. And when plants are consuming nitrogen, it's almost most of it is nitrate that they're consuming. So this liquid is going to extract all the nitrate from the soil into the solution, such that when you filter the solution out, you've got virtually all the nitrate. And then what you want to do, you want to look in that solution and look at the concentration of nitrate to see how much nitrogen was in the soil. And the concept how that works is really pretty simple, and I'm going to demonstrate it like this. Here are 2 things of tea. They both contain the same amount of water, but one was made with more tea leaves. And you can just look at this and tell which one has more tea. This is the weak tea, this is the strong tea. This had just a few tea leaves, this had a lot of tea leaves. And what you're doing when you're saying this is darker and so it has more tea leaves, you're basically, when you say it's darker, there's light being emitted from somewhere. That light is going through the bottle, and some of it is being absorbed by the tea, and some is traveling to hit your eye, the receiver. So there's an emitter, a receiver, and something in between that's going to absorb some of the light. Well, that's how this machine works. It's going to take that liquid solution that contains nitrate, and it's going to bring it to a place where on either side there's an emitter of light and a receiver of light. And the emitter is going to emit a very specific wavelength of light. And it's going to travel through the solution. And the more nitrate that's in that solution, the more of that light it's going to absorb, and the less light that's going to hit the receiver. And so it's basically going to measure the nitrogen content of the soil. by how much or how little light reaches the receiver after traveling through the nitrate solution. In addition to measuring the nitrogen content of the soil, most farmers are always going to want to know the phosphorus content, the potassium content, and they may want to know other things like the copper and boron content of the soil. To measure those nutrients other than nitrogen, they use this, what they call an inductively coupled plasma machine. I think this is the coolest part of the soil test lab. The technology is just mind-boggling. And it works like this. First, they take some of that dry matter of the soil sample. That's just dry matter. Then they're going to mix it with some liquids, a solution. And what that solution is going to do, it's going to take all of the plant available nutrients, from phosphorus to potassium to copper to everything, and it's going to extract it from the dry matter, such that when you filter out the liquid, it has all of the plant available nutrients that was once in the dry matter of the soil. Then that liquid is going to come to this machine and it's going to be sprayed as a fine mist into a chamber. And in this chamber, it is intensely hot. And I'm not exaggerating when I say there's a part in this machine that is literally hotter than the surface of the sun. Now, if you're like me, that sounds unbelievable. I thought people were pulling my leg when they first told me this, because you think, if something in there is hotter than the surface of the sun, why isn't it melting the machine? Why isn't it melting all of us? I've got a way that I've made sense of it. This isn't technically correct, but it's how I've come to think about it. They're spraying that fine mist of liquid that contains all those plant available nutrients into an intensely hot environment where they also add argon gas. Now, there's something about that mixture and the way this machine works that it creates something that's like a floating fireball. And I say floating because although it's really, really hot, it's not touching anything, so it's not burning up anything. And it's also that floating fireball, it's not exuding much heat at all. There's very little heat escaping, so that's why it's not melting anything around us. Now, what is important is not how that heat is created, but why we heat it in the first place. To know why we burn those nutrients at such intense levels, we have to remember what we learned in high school about the structure of an atom. So remember the atom. It has a nucleus in the middle, and then there's electrons orbiting that nucleus. And each different element will usually have a different number of electrons. And those electrons are going to orbit at a natural level, natural distance from the nucleus. Now, when you take any of these atoms and heat it up, the atoms are going to absorb the heat, and it absorbs the heat by those electrons expanding their orbit, doing an orbit at a greater distance from the nucleus. But those electrons don't want to be that far from the nucleus. They're going to want to go back to their original natural level. And when they do, when they collapse, they're going to release some of that energy, and it's going to be released in the form of electromagnetic radiation. And what's important is that because each atom has a different structure, when those electrons collapse and emits electromagnetic radiation, each element is going to emit electromagnetic radiation of a different wavelength. Now, you've actually seen this, because one form of electromagnetic radiation is just light. There's a certain interval of wavelengths of electromagnetic radiation that we can see. And within that interval, as the length gets bigger and smaller, it appears to us as different colors. This is why when you burn different things, they emit different colors. When I light this lighter, it's burning a fuel such that when those electrons collapse, it's emitting electromagnetic radiation of a particular wavelength, not only that we can see, but we see as yellow. When you turned on an electric stove in your house and made it really, really hot, it usually turns orange. Well, those are electrons that are collapsing, emitting electromagnetic radiation of a particular length that you can see and that you see as orange. When I turn on our natural gas stove at home, it emits a blue light because it's burning something different. It's burning natural gas. And there's even, if you burn strontium salts, it'll emit a red flame. If you burn a methanol and boric acid, it will release a green flame. So when you burn different things, the substance that you're burning is revealed in the color of the light you see, which is just different wavelengths of electromagnetic radiation. Now back to this machine. Remember, we cannot see most wavelengths of electromagnetic radiation, but this machine can see a lot of things that we can't. So when it burns those nutrients, the electrons expand and then collapse, and when they release electromagnetic radiation of a particular wavelength, this will detect it. If calcium releases its wavelength, it can detect from that wavelength that calcium is there and how much calcium is there. When phosphorus emits its wavelength, it can detect that phosphorus is there and also how much phosphorus is there. And so from this amazing technology, you get a wealth of information about the nutrient content of the soils. For plants to be able to consume nutrients from the soil, a number of chemical reactions have to take place. And so the soil must be right to facilitate those chemical reactions. It has to have the right environment. And one way of measuring a good environment for plant production is the pH level of the soil. Now you're probably familiar with the term pH. Perhaps you saw it in shampoo commercials. Perhaps if you have a pool and you were doing analysis of the chemicals in the pool, maybe you measure the pH level of the pool. But farmers are often going to want to know the pH level of their soil. Now what is pH? pH basically just measures the concentration of hydrogen ions in the soil. And a good soil is not going to have too many hydrogen ions or too few. There's a range in which there's just enough hydrogen ions to let plants consume nutrients. And so when they send the soil sample here, they want to measure the concentration of hydrogen ions in the soil. And this is the machine that does that. And it basically works like this. It exploits the fact that a hydrogen ion is simply a proton. You might remember that a hydrogen atom is just one proton, no neutron, and one electron orbiting it. But if you take away that electron and you only have a proton left, that's a hydrogen ion. And since it only has a proton left and that proton is positively charged, a hydrogen ion is positively charged. Now I want you to think about the way a battery works, if you ever learned it. A battery works by having one side containing positively charged materials and another side containing negatively charged particles like free electrons. An electron out there on its own is a negatively charged material. And a battery works by allowing those negatively charged objects to move towards the positively charged objects. And as those electrons move over to the positively charged objects, those movement of electrons is an electric current. That's literally what an electric current is. And so what this machine does is it takes the hydrogen ions in the soil sample and it measures the strength of the electric current that it can facilitate. So if you have just a few hydrogen ions in the soil, then it can help move some electrons and it can facilitate a charge, but perhaps a weak charge. But if you have a lot of hydrogen ions in the soil, it can facilitate a much stronger current. And therefore, this would be a high concentration of hydrogen ions. This would be a low concentration of hydrogen ions because this one could facilitate a stronger voltage. Now we've said that pH just measures the hydrogen concentration of a soil, but the pH index works like this. I'm going to show you the formula for it. It goes pH equals -1 times the logarithm of the concentration of hydrogen ions in the soil. And if you take pure water, and pure water is not just H2O, it's H2O plus some hydrogen ions in there. And if you take the hydrogen ion concentration of pure water and insert it into that formula, it's going to spit out a pH of 7. And because of that, we consider a pH of 7 to be a neutral pH. Now, if you have a soil whose hydrogen concentration is greater than that of water, and you plug it into that equation, you're going to get a pH level less than 7. And anything less than 7 we would call an acidic soil. And that is one of the main problems with cropland. If you take a field that's been farmed over and over, it's going to accumulate more and more hydrogen ions in the soil. When you measure the pH, when this machine measures the pH, that pH level is going to go down, and it can go down far enough that plants have trouble growing or may altogether stop growing. And if that's the case, if farmers find their pH of the soil is getting too low, what they'll usually do is apply lime. They apply lime to the land, and it reduces the concentration of hydrogen ions, increases the pH level of the soil. Now, if you have very few hydrogen ions, less than that of pure water, and you stick it into that formula, you're going to get a pH level greater than 7. We call that alkaline. You can have trouble with that in some soils, not around the soils that I'm used to, at least around Oklahoma and South Carolina.